just cover the lateral bipolar transistor and vertical bipolar transistors as written in the text. You can just refer to it. And but I have we have discussed about the general base transport, and I have a summary of that, which is we just put. Let me see. Is it okay? These letters are clear in the screen? Okay, the summary, we put the emitter base electric field 0. The current is 0, it's minimal, so we can get the electric field existing between emitter and the base, and then with that electric field we apply in this equation to get the electron current, which has to be injected to the base and collected at the collector. And then we end up with this equation, which is simple. And here the nominator in this equation, this is corresponding to the total base doping, total amount of the dopants in the base. This is nothing but the total amount of dopant in the base, and that is going to be called the Gumbel number. Okay. So according to this equation, in order to have a big current in a bipolar, we have to lightly dope the base to make this thing, the whole integral of this, small, right? So that is the basic equation for the general transport in the bipolar transistor. And then we skip the charge control model, and then we go for the current gain, which is going to appear in the next chapter. I arranged that in the next chapter. The bipolar transistor operation 2, and then the first topic is going to be the current gain. And we have 3 elements: recombination in the neutral base region, and hole injection into the emitter, and finally emitter base space charge region recombination. And take all these 3 factors into account, and as a whole we end up with this curve. And the low level of the base power, the space charge region recombination dominates the whole injected current, and then most of the base emitter voltages we have injection current, and then at the later part we have a roll off of the beta, which means decrease in the base current because of the resistance problem between the emitter and the base. Okay, so we are going to talk about the resistance problem later. And then after we current control the current gain, we move to the charge control. We have to move to the charge control model here. And then in the last lecture, we just covered the two aspects of the charge storage in the bipolar. One is injected minority carrier charge induced diffusion capacitance, which is the capacitor coming from the fact that minority carrier has to be injected in both sides of the emitter and the base. So we have diffusion capacitance. And then another charge storage is the space charge induced junction capacitance, which means since we have a space charge like this space charge width is going to be modulated with the application variation of the emitter and base voltage. So that's time-dependent charges is going to happen in this capacitor, in this space charge region. Okay? So we made a comparison of those two, and then we put the real numbers, and then we end up with this charge in the y-axis and then voltage of emitter and base. We have seen that the diffusion charges is going to increase with the voltages in this exponential dotted line here, and the space charge charges is going to increase like this, in this fashion. So this means that at the small voltages, the charge space charge will dominate the whole process. But after a while, as the emitter base voltage increases, now the diffusion injected minority carrier charges is going to control everything. Okay. Up here we have discussed in the last lecture, and today we're going to introduce the charge control model. Well, the objective of this model is to drive a set of equations for terminal currents as a function of charge and time dependence of the charge. The variation of the charge is, you can say, this is related to the capacitance. So the charge variation with respect to the time, right? And first we define the charges in the base, forward bias base, and emitter, and reverse bias charges in the base, and the collector charges. The forward mode and the reverse mode. And then approximate the charges with just two charges, which is QF and QR. So we add those two charges, which comes after the forward bias, QBF and QE, into just a small QF. And then the reverse charges, QBR and QC, we put all those things into QR, small QR, okay, to make the whole equation simple. And then express the terminal currents as a function of these two charges. So let me give you the result first. Here, the express the terminal currents as a function of these two charges means we want to deduce some equations, something like this. The terminal current to the base is just this equation. This tower is the characteristic time, which is going to be defined later to make this equation okay? And then in the reverse mode, the base current, the terminal current, is going to be QR over tau BR. This is a simplified equation, right? Then emitter current is QR over tau R, and here the collector current is going to be This, by the way, the direction of the current is just the opposite of the direction of the electron movements. Okay? So when you say current is going through this way, it means that electrons are moving from this side to this side. Okay? Now, the collector current is QF over tau F. So basically, we want to deduce these four equations: 1, 2, and 3, and 4. Okay? So we want to deduce the terminal current at each terminal with this simplified equation. How can we do that? Now, the first step is just in a forward mode, we put these two charges into small qf, and then in the reverse mode, we want to put these two charges in small qr. And in order to do that, we know this collector current can be expressed in this fashion. We have derived that in the last lecture. And then in the base current in the forward bias can be expressed as this. This M1 and M2 and this is actually, it should be N1 and N2. There's a misprint here. Okay? It's just to put no, this may be right. This whole exponential thing is going to be simplified with a symbol, M1. It stands for, this M1 stands for this equation, just that, okay, to make this whole thing simple. So the collector current can be said diffusion coefficient of space charge region and M1, something like that. Okay, here the base current in the forward mode, forward bias, can be expressed just the diffusion coefficient of the hole and the emitter side space charge length. Okay, and then M2. M2 is just this. I think. Yeah. M2 is Pn not exponential. That is going to be M2. Okay, here M1 is NP not and exponential. This is going to be M1. And QF is going to be that, and the QE is going to be represented with that equation. That we know in the last lecture, in the last discussion. And then the important thing is the QF is a summation of these two charges, and then we know the Q is very much smaller than the QBF because of the doping levels. Okay? So we have big charges in the QBF. It's lightly doped and a very big space charge region. And then here the emitter side, we have a very narrow space charge region, so that the Q is almost trivial. So QF is almost set to the QBF. And QF is IC or tau F, that the charge is going to be the current times the specific characteristic time. And then with this definition, the tau F is going to be expressed something like this with equations given here. Okay? So this tau F can be nothing but the space charge region in the base square over the diffusion coefficient of electrons. And define QF is with the collector current is going to be QF is going to be represented like this, and QF is going to be represented like in this fashion. It's just similar. It can be QF can be expressed in terms of the base current and the base characteristic time, and with this equation, it ends up with this base characteristic time is going to be expressed in this equation here. Okay? So, if you want to say this QF is the multiplication of the collector current and the characteristic time, and the characteristic time is going to be end up with this equation. And if you want to say the charges QF in terms of the base current, not in terms of the collector current, then here the characteristic time is going to be expressed like this. Okay? Then all we have to know is we have to find out what is the tau F and what is the tau BF, what is the relation between those two. And we define now tau BF, tau F is related with the gain, beta, the beta we know. And with this equation, we end up with the IC, collector current, is going to be base current times the beta, gain. That's beautiful, right? So it's consistent in a way to say the collector current and the base current relationship is going to be related with the beta F. And that is the definition. That's what we call the gain, the beta, right? And then we can maintain this equation with all this terms. And then this is this is for, I think it's for the reverse mode. That is for the forward bias case, and the reverse bias case, we have to think the collector and the base. Okay, with this charges, injected minority carrier charges, going to be expressed like that, and then just like the forward bias case, we have emitter current and the reverse base current, and the charges corresponding to all those things, and then we lump the two charges into one charges, QR, which can be approximated with the QC in this case. QBR is trivial. And the QR is going to be expressed something like that. It's just like the former derivation. And QR is also, it should be expressed in that fashion, and then we have to have these relations. The beta is going to be, it has to be defined as IE over IBR. So we have to maintain this equation, and then we end up with all these equation relations, which is consistent from the definitions. Okay, so that's it. Just a explanation of those. And then in the summary, what we try to do is, in a forward bias, we have two charges, and then this two charges is going to be lumped to the QF, small QF, and then with this, we set the characteristic time, which should be consistent in a way to say the current is going to be the charge divided by the characteristic time. And this characteristic time derivation now is important, and then between these characteristic times we can find the relations, and then actually if you find the relationship between the tau F and tau BF, it's not it is given it should be inconsistent. Say tau BF is related to the gain again with tau F in this fashion. Okay, this is a current. Current is the same thing. The gain has to be defined in terms of the current as well. It's just exactly the same. Okay, and then reverse mode, we have two charges, something like this, and then this two charges going to be lumped into the one charges, small qr, and then the terminal current now in this case can be expressed with a characteristic term like this. So as a whole, what you can see is that this is the terminal current, and then the current in between those two terminals is going to be said with this equations, the charges divided by the characteristic time. And this characteristic time is going to be defined according to the parameters of the bipolar transistors itself. Now, this is the collector current and emitter current and the base current, which is, we derive the models here. Now, with this DC model, we have to think another one, which is the charges dependent on the voltages. Time-dependent charge has to be added to this DC steady-state charges. Okay, this time-dependent charges is related to the diffusion, minority carrier diffusion capacitance, and the space charge capacitance that we have just discussed a minute ago, right? So those two charges is going to be added to this DC steady-state charges states. Okay, so that's a simple, in a way, to. This is the emitter base. You have a DC charge control, charges, current, and then there's some kind of charges related to the variable with respect to the time, okay, the space charge and the diffusion charges. So all you have to do is just add those two things, and then, for example, in a collector current, the DC IC, which we have discussed a minute ago, and then you just add those two terms. The one is the diffusion, minority diffusion charges, and this is a space charge. Two charges which are time dependent, right, in a bipolar transistors. So those two things is going to be added to the collector and then emitter. And in the base, those two charges separately related to the base current, something like this. This is a very complicated, but rarely will we solve this equations as written. We don't have to. However, they do serve to useful functions. Yeah. So that's the things that we have to say about the charge control models. We have discussed the DC, and we have discussed over the time-dependent charges, which has been added to this. And then there's a time-dependent charges has two things. One is a space charge, and the other thing is injected minority carrier charges. And the final thing we should talk is a saturation. Now, if you have a base, emitter base forward bias and base collector reverse bias is the normal situation. But what happens if you have forward bias between emitter and base and the forward bias between emitter and collector? Then in the base, every charge is going to be added up. And then this saturation means, it literally says, some part there's no increase in the current, even though you increase the voltages to the system. That is the saturation. And how it happens? Now, before the saturation, this is the normal definition. The base current, if you multiply the base current with the gain of the system, then you're going to have a collector current. In other words, the current that you can have is divided by the base current, and that is going to be, we call the gain. This base current is the input. The collector current is the output, right? So the output has to be input times the gain, something like that. That is the definition, right? Now, the edge of saturation means beyond this voltages, the current is not increasing, and the edge of that voltage is the voltage that we can have this relations right. Okay. If you cannot have have that relations between base current and collector current anymore, then we call that voltage is that is the edge of the saturation. For example, I have given you the example at the now. This is the base current that is measured, and then this is a collector current. And then let's say if you have a 10 microamps in the base current, you're going to have a collector current of 0.5 milliamps. Okay? And then you increase the base current to 50. Of course, you are going to have increase in the collector current in 25. 100 is going to be 5, and 200 now it's going to be 10 milliamps. Now, if you increase further to 500, then this collector current is not going to increase anymore. It is saturated to 10 milliamps. So if you increase the base current more than this, after this, the collector current is going to be saturated to the values 10. That is going to be called the saturation. And then this situation, this base current, okay, we call that the edge of saturation. Just you can say this is a threshold or whatever, the starting the saturation. So from the device point of view, and more specifically the charge control viewpoint, the charges look like this. It means that we have a charges QF here, and then with the slope is going to be related to the currents that we have, right? And then as you increase the base current, this slope is not going to change. It maintains the same slope, and then just the level is going to be increased with the increase of the base current. So that the slope is related to the current between the emitter and the collector, so that even though you increase the base current, it just increase the total amount of this QF, not changing the slope, so that the current is going to be saturated. It's not going to be any more than this. Okay? So the above observation suggests that in saturation one can look at the shaded charges specifically beyond the edge of the baseline. So, well, these charges, increase in the charges QF like this, it is not going to contribute anything to increase in the current between the emitter and collector. So this saturation phenomenon is not good for the device functions. Well, if you work in the DC mode, no problem. But what happens if you want to use this device as a switching mode? If you put some input on this so that you have a steady current, steady state current as an output with the base input, now if you want to change it, then this device is not going to make a proper response to the input until this stored charges is going to be eliminated. So if you just reverse the bias on this system for the switching, then this bipolar transistor is not going to work until everything, the stored charges, is going to be eliminated from this. So let me give you the result first. The example here, this is a typical example. You put the T1 in a steady state, you have a certain current, and then you just switch it to some other part. Then the system is going to go like this, and then at this T1, the stored charge is going to be eliminated. And then it begins to respond with the input after this 2.37 nanosecond. That means it's a delay. So this saturated charges is not actually good for our system operation, but it's inevitable. Okay, let me discuss about the stored charges in next week on Monday, and then we finish up this bipolar transistor and the MOS transistor operation principles, and then we're going to have a final lectures on Wednesday, right? On the final lecture on the Wednesday, probably we are going to discuss a little bit about thin film transistors, which is totally different from this wafer transistors, okay? And then on that Wednesday, I'm going to hand out you the past exam, and it's not going to be the same, the one on the final exam of use, but you can just review those, okay? Refer to it. And then 1 week that week, and then 12th, which is Monday, we're going to have a final. And then the final is just at most 1.5 hour. It's going to 1.5 hour. It's going to be allowed to do the exam. Okay? Okay, I'll see you on next week then.